So do you remember when we did that lengthy limit definition to find the derivative, the slope-giving function of some curve f of x? I do, of course, right? It was great fun and crazy long. So there's got to be a better way, right? A shorter way. And that's what this lesson's about. Just like progress in all walks of life, you say there's got to be a better way. And so we go and we find that progress, and that's what we're going to do. So we're going to find what's called the shortcut. It's an informal way of putting it, to finding derivatives or doing differentiation. There's a whole bunch of rules that go with that, so let's dive into it. So you've got f of x equals x to the n, meaning you've got any function where you've got x raised to some integer, right? Or eventually you're going to see some fraction works too, so really any real number up here. So x to the 7th is a real easy example of that. How do we find the derivative with the shortcut? Well, you multiply everything by n and then subtract 1. So essentially it becomes nx to the n minus 1. That's it. That's the pattern. How does that work with numbers? Well, you'd do what a lot of teachers call power down. So we multiply by 7. That 7 comes out front, if you will. And then subtract that value by 1. 7 minus 1 is 6. 7x to the 6th is your derivative. Oh! How quick is that? That's it. I promise you. Another rule we're going to go over is whenever you have a function equals a constant, the derivative, dy dx, I'm giving you different notation here, is equal to 0 every time. So if I give you y equals -2, the derivative of a constant is going to be 0. Done. It's pretty sweet, right? Now we're going to go over the why behind why these work at the end of this video. So I'm going to come back to it. For right now, I just want to practice you in the art of the shortcut. It's pretty sweet, right? Take a deep breath in, deep breath out. That's us relaxing because we don't have to do long-term crazy limits anymore. You still need to understand them, but there's a better way. So this says let's practice with these newfound rules. Find the derivative of each function below. Remember, the derivative is still the function that gives you the slope of the original function at any x value. It's just we're taking a lot less time to do it. So we want f prime of x, in other words. So f prime of x is equal to, we multiply by 3, so that's going to be 3x, and subtract 1 squared. Power down, 3 comes out front, and subtract 1. 7x to the 5th. How do we deal with the 7 there? No sweat. I'm going to write this as y prime. You can do dy dx as well. 5 times 7 is what you're doing. So I'm going to write all of that out. So that 7's just chilling out, just hanging out. So you get the 5 comes out, x to the 5 minus 1, which is to the 4th. And we simplify. 7 times 5 is 35x to the 4th. So anytime you have a coefficient there, it's just hanging out. Well, what do we do if we have a fraction? Does it change things? No, not at all. So we use our power rule. So g prime of x is equal to 1/2 comes out front, 1/2 times x to the 1/2 minus 1, which is -1/2. 1/2 minus 1 being -1/2. Some teachers will want you to rewrite this as 1 times, well, it's just a 1 up top now, all over 2 x to the 1/2. And others will see that as 1 over 2 root x. All correct answers. For now, just get this down. It's sweet. It's the power rule. Again, what we're using? X to the n. The derivative of that with respect to x is equal to nx to the n minus 1. Oh, it's beautiful. Let's keep going. The derivative of this polynomial. Well, when you have more than one term, what do? You take the derivative of each piece. Because it's all being separated by subtraction and addition, we can take the derivative of each part. So the derivative of 4x squared is 2 times 4 is 8. 2 minus 1 is 1. So just 8x to the 1, or 8x. Minus 5's just hanging out. So what's the derivative of this? Well, this is technically, if you will, it's like we're doing 5x to the 1. 1 times 5. X to the 1 minus 1. Well, x to the 0 is, well, 1. So that's going to be equal to 5. So that's why that derivative is 5. And then the derivative of a constant is 0. So that's just plus 0. That goes away. So I'm going to write this off to the side just so you have this here later if you're taking another look at the notes. The derivative of 10 is equal to 0. It's a constant. That's it. So again, Got subtraction or addition? Take each individual term and take the derivative. We'll do it again. W prime of t, let's rock and roll. We're taking the derivative of this with respect to t. So I multiply by 4, 4t, and cubed. It's cubed because it's 4 minus 1. Minus, the 9's just hanging out. I'm going to do this in steps. 3 times t. 3 minus 1 is t squared. And then minus 72 is a constant number. The derivative of a constant is 0. Let's simplify this down. We'll get 4t cubed minus 27t squared. And that's all that problem wrote. Oh, it's beautiful. Keep going. Can you imagine how long it would take to do these problems if it was with a limit? It's crazy. The derivative of a constant, f of x equals 4. That's a constant. The derivative of that is 0. That's it. Done. And last but not least, we've got one more little polynomial to rock and roll with. Taking the derivative of y with respect to x. 2 times negative 12 is negative 24. 2 minus 1 is what we get up in our new power, so that's to the first. So I don't put down a number because it's to the first power. Plus 7x, we already saw here that when we have a power of 1, imagine that there's a 1 there. You're doing 1 times 7 is 7. X to the 1 minus 1 is x to the 0, which is 1. And so we're done. That's beautiful. So if you've got a teacher that's not teaching you the why, or you're in a Calc 101 class and you don't need to understand the why behind it, then you're done. You've got down your rules. One thing to mention, before I get into the nitty-gritty of the why, is the reason why we're able to just take a derivative of each part of a polynomial separated by subtraction or addition is because the derivative, as we know from our previous videos, is a limit. And we're allowed to take limits by taking the limit of each piece when separated by subtraction or addition. The same thing works with differentiation. Very cool. All right, here's for the why. It's a little bit more behind that. So why is it that when we take a derivative of a constant, we get 0? Well, it's a couple different reasons. One, you could just plug this in to the limit definition of the derivative, the formal definition, and you'd get 0 every time. Or we could take a look at it conceptually. What does the graph of a constant look like? Well, the graph of a constant is always a horizontal line. So let's take y equals negative 2, for example. Y equals negative 2 looks like this. It's a horizontal line with a slope of 0 everywhere. So any constant has a slope of 0. And what is the derivative? It's the slope of that function. So the derivative of a constant is 0. I think that's a nice way of understanding it. Now, graphically, it's not as easy to conceptualize why it is that our power rule works. This is what a lot of people call the power rule. All right, it's one of the basic main rules that we're going to use there, right? So the power rule. So looking at that, how do we exercise why it works? Let's actually use the limit definition of the derivative. So if I take the limit as, we'll use h. H goes to 0 of f of x plus h minus f of x all over h. The question becomes, the derivative of this, why does it equal out to that? Well, you get the limit as h goes to 0 of, we're going to plug x plus h into f, just like we did in a previous lesson. And if you're still confused on this step, please go back and watch the lesson in 2.1. Super critical. Minus f of x, which is minus x to the n, all over h. What we want to get out of this is this formula. So that's what we're going to get. So this would be equal to the limit as h goes to 0. X plus h to the n, it depends on what the power of n is. But in general, it expands out to be something that looks like this. And this is one of those where you're going to have to trust me. It's called the Binomial Theorem. So we expand it out. You get x to the n plus, and then h comes into play, right? So what we get is x, well, actually, we get a polynomial first. We get a bit of a, well, the whole thing's polynomial. We get n, get a coefficient, times x to the n minus 1, interesting, times h, plus, and then the next one, I believe, is going to be n times n minus 1 all over 2. That's our coefficient times x to the n minus 2, h squared, plus, and it keeps on going on and on like that until our final term is actually h to the n, all over h. Now, why does this matter, this h and how everything's done? Well, Let's check it out. Oh, I forgot the minus x to the n. How could I do that? We got the minus x to the n. So x plus h to the n is this whole expansion. Minus x to the n is this. The x to the n's, they cancel. We're just engaging in some good old-fashioned limit simplification. So that cancels. And look what every single term now has. Everything in it has an h. So you get the limit. Let's change to orange. Why not? As h goes to 0 of h times, I'll factor out an h, nx to the n minus 1 plus n times n minus 1 all over 2. And that's x to the n minus 2 times h. We still have an h left because it was h squared, plus this next term will have an h in it as well still. This will be h to the n minus 1 because there's one less h, which we factored out. But here's the important part. Every other term has a higher and higher h value in it. The only term that doesn't, as the h's divide out, is this first term. So when we take the limit as h goes to 0, everything with an h in it, which is everything here, becomes 0. And so you're left with nx to the n minus 1. So all the other terms cancel out. You're left with your formula. That's beautiful. So from here on out, when the question becomes, how do we get that formula for taking a derivative of some kind of function? It's going to come from this limit definition, the derivative, the quotient, the difference quotient. All right, for now, I'll see you in another video, but that was a rad exploration of why. Peace.